Before we tackle graphical method, let us first understand linear programming. What is linear programming? We know what linear means. We see examples of problems that have linear constraints, like plotting linear equations. Now, we're to add an extra ingredient, some quantity that we want to maximize or minimize. Quantities like profit or costs. If the quantity to be maximized or minimized can be written as a linear combination of variables, this quantity is called linear objective function. This means that linear programming is the business of finding a point in the feasible region for the constraints, which gives an optimal value for the objective function. If the linear problem involves two non-negative decision variables, x and y, graphical method is used. From the name graphical, we utilize a graph or a Cartesian plane. Since the two decision variables, x and y, are non-negative, we consider only the first quadrant of the Cartesian plane, the positive side of the Cartesian plane. Step 1. Define the constraints. All the constraints relevant to the linear programming problem need to be defined in the form of inequalities. Greater than, less than, greater than and equal to, greater than, less than, and equal to. Wait. Anyway, moving on. Step 2. Define the objective function. What is the objective of solving the problem? Is it to maximize profit? Maybe minimize downtime? Step 3. Highlight the feasible region on the graph. But this does not answer which point is the maximum or minimum quantity. However, there is a theorem that helps us answer this question. It's called corner point. This leads us to our fourth step. Step 4. Find the optimal point. Corner point is a method that can be used to solve for the optimal point. What is a corner point? It is a point that falls along the corner of a feasible region. We use this method because the optimal point is along the gradient of the feasible region, where the objective is to maximize.
A workshop has 3 types of machines, A, B, and C. It can manufacture 2 products, Product 1 and Product 2. All products have to go each machine, and each one goes in the same order. First to the machine A, then to B, then to C. The following table shows the hours needed at each machine per product unit, the total available hours for each machine per week, and the profit of each product per unit sold. We begin by summarizing the information needed to formulate and solve this problem. The decision variables that represent the actual decisions we will make are defined as x1 is equal to the product 1 to be produced weekly, x2 is equal to the product 2 to be produced weekly. Objective function is maximization problem. We need to find the value for x1 and x2. The value should be greater than or equal to 0, which means positive value only. Constraints represent the number of hours available weekly for machines A, B, and C respectively, and also incorporate the non-negativity conditions. The objective function is maximize z is equal to x1 plus 1.5 x2, subject to the constraints 2x1 plus 2x2 less than or equal to 16, x1 plus 2x2 less than or equal to 12, and 4x1 plus 2x2 less than or equal to 28. To represent the first constraint graphically, 2x1 plus 2x2 less than or equal to 16, we must first graph the equality portion of this, which is 2x1 plus 2x2 is equal to 16. To find 2 points on the line, let x1 is equal to 0 and solve for x2. So 1 point on the line is 0, 8. To find the second point, let x2 is equal to 0 and solve for x1. For the second constraint, x1 plus 2x2 is equal to 12. Let x1 is equal to 0 and solve for x2. So one point on the line is 0, 6. To find the second point, let x2 is equal to 0 and solve for x1. For the third constraint, 4x1 plus 2x2 is equal to 28. Let x1 is equal to 0 and solve for x2. So one point on the line is 0, 14. To find the second point, let x2 is equal to 0 and solve for x1. To find the optimal solution, we will illustrate the elimination method. To begin the elimination method, we will select 2x1 plus 2x2 equals 16 and x1 plus 2x2 equals 12.
A winemaking company has recently acquired a 110 hectares piece of land. Due to the quality of the sun and the region's excellent climate, the entire production of Sauvignon Blanc and Chardonnay grapes can be sold. You want to know how to plant each variety in the 110 hectares, given the costs, net profits, and labor requirements according to the data shown on the screen. Suppose that you have a budget of 10,000 US dollars and an availability of 1,200 man days during the planning horizon. Formulate and solve graphically a linear programming model for this problem. Clearly outline the domain of feasible solutions and the process used to find the optimal solution and the optimal value. The first step is to assign the decision variables for the two kinds of grapes to be produced. X will be the hectares intended for growing Sauvignon Blanc, and Y will be the hectares intended for growing Chardonnay grapes. Next is to formulate the objective function. Since the goal of the company is to gain high revenue, we will be using the values under the net profit column as the coefficient in our objective function variables, which gives us maximize z equals 50x plus 120y. Then we will define the constraints relevant to the problem. In this case, there are 4 constraints, which are the following: x plus y less than or equal to 110, 100x plus 200y less than or equal to 10,000, 10x plus 30y less than or equal to 1,200, and lastly, x and y is greater than or equal to 0. We will now convert the constraints to linear equations so we can calculate the x and y intercepts and plot the coordinates of the lines. To find the x-intercept, we will set the value of. For example, in solving for the first constraint, first we have to convert the inequality to a linear equation by simply changing the inequality sign to equal sign. That now becomes x plus y equals 110. To solve for x, we will set y to 0, which gives us x plus 0 equals 110, resulting to x equals 110 and y equals 0. These values will be the coordinates of point A. Then we proceed to solving the y-intercept, and this time the x value is set to 0, which gives us 0 plus y equals 110, with the coordinates 0, 110 of point B. We will now continue to repeat these calculations on the remaining constraints as shown on the table. After identifying all the coordinates, we then plot this on the graph as shown. This will show us where the constraints intersect, which helps identify the feasible region. To get the coordinates of the point intersecting the lines of the cost and man-days constraints, we will be using the substitution method by solving for x in equation 1. The table shows the feasible points along.
And that's all for today. We hope we help you with our discussion.
Tune in next time for more lessons on operations research.
This is Mac.
See you next time. Bye!